continuing our scientific chemistry journey with my science project over the states of matter. And just to kind of kick us off, I thought I would start by describing what are the states of matter. And the three states of matter are a gas, a liquid, and a solid. And I was going to start by giving kind of a textbook definition of what a solid, a liquid, and a gas are, because that definition would be dependent on how the molecules flow within that substance. So in a solid, the molecules will be in a fixed position, which basically means they will be together. And I have this example. So all of these cubes represent one molecule, and you can see as I move this, they are staying together in that position. They are not moving. And so what that means is that these molecules will be very rigid and they will not have any compressibility. They have a fixed shape and volume and they cannot flow. So then next we have a liquid, and a textbook definition of a liquid is a substance composed of molecules that move freely throughout themselves, but they don't separate. So as you see, all of these molecules in here, they have a high density, so they are sitting on top of each other, and you can see they have they are not rigid and they do not have any compressibility, and they do not have a fixed shape even though they have no compressibility. So as you can see, as I pour this into this, they will take the shape of that container. So additionally, they have a fixed volume, so whatever the volume is in here, it will be the same in here, and they are pourable, so they're basically, that means that that's a fluid that can flow. And lastly, we have a gas, which is a substance with perfect molecular mobility. So this will be a low density of molecules throughout here, and they will spread out to fill their container. So this is not rigid, but it is compressible, unlike the other two. It has no fixed volume or fixed shape, but it's defined by the way that the molecules can flow, which basically means that it's a fluid, just like a liquid. And again, like a liquid, they will spread to fill the container. We're back, and welcome back to my science project. And for the next part, there are some terms that you definitely just need to have memorized going through, just to do your phase diagram and your heat curve, which we will get to later, I promise. And so those are kind of the phase changes that the states of matter will go through when they're, for say, like changing from a solid to a liquid, or a liquid to a gas, or anything. So those would be, these are these definitions. So going from a solid to a liquid is known as melting, and I'm sure you guys probably know what that is. You guys have seen snow melt and stuff like that. Going from a solid to a gas is known as sublimation. Liquid to a solid is freezing. Liquid to a gas is evaporation. Gas to solid is deposition, and gas to liquid is condensation. And it is important to note on here that sublimation and deposition actually do skip a phase. So you would expect for any phase change for it to go to a solid, to a liquid, to a gas, or from a gas to a liquid to a solid. And actually in those two steps, it will, in sublimation, it will go straight to a solid to a gas, and in deposition, it will go straight from a gas to a solid. So that's just important to kind of know. Hey, didn't see you there. Sorry about that. Today we're going to talk about a phase diagram, and this is what it looks like. It's really magical in the life of a chemist, and it talks about how a gas or a solid or a liquid can change forms, in fact, actually. So here you see on the solubility curve that the x-axis is the temperature and the y-axis is pressure. And in this region, actually, when it falls in here, it's a solid. And at this point, called the triple point, it can be a solid, a liquid, or a gas. However, at the B point here, it turns from a liquid to a solid. That's called the normal freezing point. And in this region, we have liquids such as water. actually. In the liquid state, it is a liquid, and at the C point, it boils. And finally here, we have the critical point. This is the temperature at which a substance can no longer be a liquid anymore, thus it will be a gas. And there you have it. That's your phase diagram. Hey, let's get back to science. Always such a thrill in the chem lab. Right now we're going to talk about the heat curve, which allows us to see the relationship of a system between energy and the temperature. In the heat curve, we will learn how an increase in energy can change a substance from ice, a solid, water, a liquid, and steam, a gas. As the amount of energy increases, this will cause the temperature to increase, thus changing a solid, such as ice, to a liquid, such as water. Here we see the change between liquid and solid. From this way, going leftward, we will see the substance start to freeze. From this way, we will see it start to melt. This is called a phase transition. A similar reaction happens here, except for you shall notice that this is much shorter and much less steep than this, such as this is much shorter than this. However, this will still change from a liquid to a gas coming up this way. Oh my gosh, what am I doing? This is a science project, but we always remember how important English is too. Welcome back. We're going to talk about intermolecular forces. They're really a great thing, you know. These are basically the forces that happen between two molecules. So there are three main types, and they are respectively in order from weakest to strongest: London dispersion, dipole-dipole, and hydrogen bonding. So first we're going to talk about London dispersion, which is the weakest type, and it occurs between two nonpolar molecules, which basically means that these molecules are being shared equally in these two elements, or molecules, sorry. And so basically these are going to be the weakest because even though these are being shared weakly, we know that the electrons are still constantly moving. And so when there's a shift, let's say, sorry, let me get a pen. This could be temporarily negative, and this could be temporarily positive for just an instant, and then this would make the intermolecular force. So that would be an example of a London dispersion. And then next there is a dipole-dipole, which is the which is the force between two nonpolar or polar molecules, which are made to maximize the negative and the positive, or the electrons and the protons. And so basically what that would be is you have HCl and HCl, and you know that Cl, just from the Lewis structure, is going to be more negative than the hydrogen. So the intermolecular force would be between here and here. So since negative and positive attract each other, that would be the intermolecular force, and it would be much, much stronger than London dispersion. And then the last one is hydrogen bonding, which is deceptive because you might note that this really is not bonding, but it is called a bond because it's just comparatively so much stronger than London dispersion or dipole-dipole, even though if you compare it to like a covalent or an ionic or a metallic bond, it is much, much weaker. It like pales in comparison to the strength of any of those. But anyway, a hydrogen bond is actually a type of dipole-dipole, but it occurs between a hydrogen and a very electronegative element. So the only ones that really fit that description are nitrogen, oxygen, and fluorine. So basically what happens in the same, it's basically the same as a dipole-dipole. So when you have these molecules, so this is water, you know that from the Lewis structure that oxygen is going to have more electrons, and so this oxygen will be attracted to this hydrogen, and it will create a very strong bond. Okay, so as previously mentioned, these are listed from weakest to strongest, with London dispersion is the weakest, and hydrogen bonding is the strongest, and dipole-dipole is in the middle. And that might seem kind of trivial, however, it does have a real-life application. So if you're trying to find between if you're trying to find if the boiling or freezing point, how the IMF will affect it, it is important to note that the higher the IMF, it will increase the boiling point and the freezing point, and it will decrease the vapor pressure. So let's say you have a polar element or a polar molecule and a nonpolar molecule, and it asks you about the freezing point, let's say. Since dipole-dipole will have a more IMF, a stronger IMF, it would have a higher boiling point or a higher freezing point, which is interesting to know. And also it is important to know if, let's say you have a question on the AP test and it asks you about, let's say, BR2 and I2. Well, you might, you might draw the Lewis structure and you'd see that these are both are nonpolar molecules. However, since I2 is a larger, the molecule of I2 is larger than it is of BR2, it will have a stronger IMF. So the larger the size also makes the IMF higher, which is that is really important to know as you are going to take your AP test in your final.